Okay, good afternoon everybody. So in which week we are now? Week 10, exactly. Which class? So that means we are not in the first, we are not in the second, we are in this one. Yes or no? So I have to go there and click. Oh, this one. First class. Oh, this one, not this one. Oh, sorry. Yes. What have we done in previous class? I always do that because I've told you that in this course things are like what? Connected, yes or no? Every class is connected with the others, and some class they are, sometimes they go back many months before, yes or no? So what did we do last class? Yes? So we were looking exactly to what? We were looking at? But what's our objective by doing that? The ID versus? Yeah, which we call the MOSFET characteristic, the IV characteristic. Excellent. The same person I asked last time and she answered again and again. I hope to hear from somebody else. What else we did? That's the main thing we did. Yes, go ahead.
We study about saturation region and...
Very good. Very good. Excellent. That's another one. Yeah. So basically we found the two areas of IV characteristic. Saturation triode. Yes?
We study about NMOS and PMOS.
Excellent. And also we studied the PMOS and NMOS. We studied NMOS since the beginning, but we introduced the PMOS because that's another device we need to study. Excellent. Excellent. Alright, so what are we going to do today? We are going to carry on our analysis. Let's have a look at that. So far so good. Alright, so today, going further on that, we have to understand things clearer and clearer. So the first thing we need to introduce is a symbol. Yes or no? The diode, the same thing that we did with the diode will be repeated with the MOSFET and the BJT. So the symbol of the MOSFET, I forgot my pointer. You can see they are A, B, and C. What's the difference? Let's go. So A is the MOSFET, is an NMOS. First of all, it's an NMOS, not a PMOS. As you can see, there are not 3 terminals, there are 4 terminals. The fourth being the body, which we do not use in our course. So that's one symbol, and there's an arrow from the body going into the gate. We can understand that in a second. Alright. The second symbol is similar to that. However, the arrow, instead of putting it in the body terminal, we put it in the source terminal, and it shows the direction of the current. Do you see that? The direction is of the current in the NMOS from where to where? From drain to source, exactly. So it comes into the drain and gets out of the source, and that's why the arrow is out of the source. Did you get that? Good. Still the body terminal is there. That's also a symbol that you can find also in the simulator when we talk about it in the circuits and etc. The last one, which is the most common one, basically we took off the body terminal. There's no body terminal there, yes or no? Where is it going? Usually actually it's actually connected with the source. And that's what we do in this course. We connect, and this also you find it in the project. You connect always the body to the source, because the body and the source must be on the same potential. If they are not in the same potential, that means same voltage, there will be problems. We are not going to study them here. To avoid them and to avoid talking about them, we just connect them together, the body with the source. Salamat salamak. Okay? Good? Very good. Now, so the arrow here in symbol C and B, it shows basically where the current is getting out. Okay? Good? Now in A, the arrow is on the body. And that means what? That means in order to create a channel between drain and the source, the gate has to push that arrow inside to allow that current to go in. Do you understand? Because we need to have VGS. What's the condition to have a channel, by the way? Who knows that? What's the condition to create a channel for an NMOS? All these symbols are for NMOS. What's the condition? Yes?
The VGS has to be more than the threshold.
Very good. VT, yes, and that's the condition that we need. By the way, what's your good name? Very good, Nas. I'm talking only to NASA out of how many? 41. So what's going on? So if you want to have a good grades, I have mentioned that millions of times, you have to revisit your class. It's not really rocket science, huh? It's not something difficult. It seems that 40 out of 41 are not doing that, and only 1 out of 41 is doing that. It's sad, but again, when you see your grade, do not blame me. I was clear, so Allah. So that's these are the symbols for the NMOS. Here, what we want to show also, that's also very important fact, and that is, in terms of device, the source, device means when you look at the composition, when we touch that device, the source and drain, they were symmetrical, yes or no? They were the same. Huh? That's physically. That physically means that something that we see and touch. But electrically, they are not different. They are not the same. The drain is always higher in voltage than the source. Why? Because the current goes from the drain to the source. And always the current goes from where to where? From high voltage to low. You understand now? So this is how we know which one is the drain, which one is the source. Even if we don't know where the arrow is. You understand? So let's say I don't show you the arrow, or you don't see the arrow. People also do that. It's not magic. They are too lazy, the engineers. Because they assume that other engineers are smart enough to understand where's the drain, where's the source. Huh? So, they just show the voltage here and here. Okay? So if the voltage here is higher than here, then this must be the drain, this must be the source. What if the voltage now change and here becomes higher than here? So this becomes the drain and here becomes the boom. That's it. Did you get the point? So the arrow doesn't mean anything actually. You understand? It shows the source to help you out. That's not always the case. Usually we keep the source always lower than the drain. But there are sometimes that the source is flipped with the drain, yes or no? So the drain becomes lower in voltage than the source. And as an engineer, we should know that also the terminals have to be flipped. But always the drain is higher than the source in voltage. Put that in brain. Take notes. Alright, good. Already. So now it's a recap time, or almost a recap time. So here are the regions of the MOSFET, and specifically NMOS. So far we are studying NMOS. When we study PMOS, that's a little bit of a kick. So we have 3 regions in the IV characteristic of the MOSFET. The first region is this line. It's called the cutoff. So this line, the equation for this line is what? This line, the line here of the cutoff. The equation is, of course, this is ID versus VDS, yes or no? So the equation for this is ID is equal to 0. Why? Because every point there has the index 0, yes or no? Yes. It can take any VDS. But what we know is that ID is equal to 0. And that's the equation. Got it? And this happens when VGS is below VT. Yes or no? Good? That's the first one. So VGS is below VT. We don't have any channel. And we have no triode. We have AC. VDS here or here or here. Doesn't mean anything. Because there is no channel. Yes or no? Very good. Now, if now VGS is above VT by a certain overdrive, then we have 2 zones, the triode, where the equation is quadratic. It's not visible here, I'll show you later. Quadratic, you have VDS squared, and that's why it's like that. And the saturation, where the current there is completely independent of VDS. Whatever VDS value there, this value is constant. And that's what we call saturation. Clear? Alas? Any question? Very good. So we have 3 zones, cutoff, triode, and saturation. As simple as that. Very good. And here we are not going to repeat ourselves. For those who want to revise, can revise. Now, Coming to the voltages, we have to know how the MOSFET is working. We have to know voltages. Which voltages we need to know? How do we know where the MOSFET is working? In cutoff or VCCS or triode? So, which voltage? Did you tell me which voltages we need to know? If I tell you, I give you voltage. Go ahead.
VGS and VDS.
Very good. That's it. VGS and VDS. These are the two voltages that help us to know where the MOSFET is. If VGS is VGS, that means VGS, this distance of voltage. If this distance is below VT, that means this bar where the voltage of the gate is below this bar where VT is. That means we do have what, Master, again?
ID equals 0.
Very good. And that zone is called?
Cutoff.
Very good. Excellent. Simple, huh? We are just graphically discussing that. Very good. So, let's say VG, the gate voltage, is above VT by what? By how much? By the overdrive. Yes or no? If we are there, then we have how many possibilities? We have two possibilities. We have the overdrive and we have saturation. Yes or no? Based on what? Based on the second voltage, that is what? VDS. Now we come to VDS. Now, if VDS is below this distance that is equal to this distance, so we bring this distance and we come here. Now, if the drain is below this distance that we copied this here, is below here, we are in? Now, if it is above this distance, which is this distance, then we are in? Give me some. Hard? Hard or difficult or what? Easy? What do you think? Easy, yeah? Very easy. But revision will help you to bring it there. Okay? Instead of dreaming. The only one there. Next time sit here. I need to talk to you here. Alright, good. Alright. Now, coming back to the MOSFET. Now the MOSFET will have its IV characteristic. That means ID versus VDS. It can be in any of these curves. Not all of them at the same time. Why? Because it will have only one overdrive, yes or no? So for any given overdrive, the MOSFET will be in one of these curves. That's it. As simple as that. Now, what we know is that once we are above the cutoff, when the VGS is above the VT, then automatically we will have two zones. The white zone here, we call it the triode, and the blue zone here, we call it the saturation. Alright, that's it. That's what it is. Very, very simple. The triode is non-linear. You can see it's square 2 of VDS. We know that equation. It's not written there. That's fine. It's actually written in the boundary there, but that's okay. And here in the saturation, the current is always constant, but it doesn't depend in VDS. There is no VDS there. Yes or no? Do you see it? Here, this is the value of the current here is equal to this. There's no VDS. Here also, here, there. Saturation by the dependence between the current and the drain voltage. Boom. They are independent from each other. Yes or no? The current is constant. VDS can take any value. The current is dependent only on the overdrive. This is as simple as it is. Now, this equation that you saw here, or that you see here, is actually the equation of the border between the triode and the saturation, which actually satisfies both the equation for the saturation, which is this level, and the triode, but at the boundary there. And that's why we can use, for example, in this case, the saturation equation, and you can see that ID is dependent on VDS. Yes or no? ID is equal, but that ID is not on these curves, on the blue curves, which is the curve of the MOSFET. It's actually, we are talking about the ID on this dashed border. Okay, that means the boundary between the triode and the saturation is actually quadratic in terms of VDS. Okay, that means the boundary here between the triode and saturation is quadratic, means power square of 2 or power of 2 of VDS, and that's why this curve is of parabola, if you remember that. Huh? قطع مكافئ. Okay, clear? That's what it is. Very simple. Very simple. As you can see here, this equation, we replaced VDS by overdrive because that's the boundary. Yes or no? Yes or no? And we call that VDS SAT. Okay, VDS SAT. So if we want to write it correctly, we should write VDS and a little bit of SAT beside that. That's the VDS SAT, where basically the triode meet the saturation, the boundary. حدود. Any question? Clear? Confused? No. It's very simple. Two areas. خلاص? Very good. Excellent. Excellent. Let's keep going. So what do I have? Here we see something really interesting. So the question is, when the MOSFET is employed in amplifier, because the MOSFET will be used as an amplifier, yes or no? And the answer to that is that the MOSFET has to be in saturation. And why? Now that's what we need to discuss now here. Okay? So the MOSFET has to be in the blue region so that we can use the MOSFET as an amplifier. It will not amplify in this region. It will amplify in here. Why? Okay, that's what we are going to discuss here. So, in saturation, the drain current depends only on VGS. It doesn't depend on VDS. And who's the input here, the input voltage? Is it VDS or VGS? The controlling voltage of the MOSFET? VGS. That's the one who controls. Off, on, yes or no?
Yes.
And the output is at VDS and IDS. Yes or no? So the output is both IDS and VDS. But here we are mainly concerned on the IDS, the drain current. Yes or no? So the drain current depends only on the input voltage, that is VGS. Okay? And look here, the current here is constant. It depends only on the input. So that means I'm creating a current source controlled by a voltage. Yes or no? Got it? Clear or no? Let me repeat. The ID characteristic here of the MOSFET here, it actually relating two output parameters. ID is an output, the drain current, and VDS also is an output. But also it can be used as an input as well, because it can also control how the MOSFET is. But in saturation, that VDS influence or control is gone. Yes or no? Because VDS cannot control this current here anymore. Yes or no? Who control it? The input voltage, that is VGS or the overdrive. They are the same thing. They are different only by bit. Yes or no? You see the picture now? So therefore, what we say basically we have a current source that is controlled by voltage. Yes or no? VGS. So we call this a voltage controlled current source. We are just put it in a nice English way. VCCS. So the transistor in the saturation works exactly as a current source that is controlled by a voltage. That's why we call it voltage controlled current source. Is it clear? So, very nice. Did you use the current source in electronics? We use it, yes or no? Of course. Now MOSFET can help you with that. Good. But you have to put it in saturation. Do you understand? You know how to put it in saturation, correct? What's the condition to put it in saturation? Condition to put it in saturation is? Wait a second. Another one.
Greater than dV over dot.
What's that?
VGS greater than dV over dot.
No. Wait, خليها. Repeat.
The VGS is greater than VDS is greater than
overdrive. And also, always, VGS has to be bigger than VT. You have to have a channel, yes or no? Because we always overlook this, so we think that is given. But we have to make sure. Very good, excellent. So, as long as we keep our VDS above the overdrive, then we are in good shape. We can use the MOSFET as an amplifier. Good? Good. Still, very good. So in this case, if we are in saturation, how this control voltage control our current? And that's what we show here in this graph. By taking the equation of the current in saturation. Is this one, yes or no? Is half Km prime W over L V overdrive square, yes or no? But the V overdrive comes from where? From VGS. Because that's the VGS, that's control voltage. V overdrive is not control voltage, yes or no? It's actually come after the control voltage, which is VGS, yes or no? Alas? That's good. So this is our input voltage that is controlling this current. This is the equation of the voltage controlled current source. Means what? The MOSFET in saturation. Clear? Good enough? Very good. It's a quadratic equation too. That means if VGS changed by anything, it will go square to influence the current. Yes or no? Very nice. That's very nice. So it's like amplifier here. Yes or no? And that's where the amplification comes from. Because the relationship between the current and the control voltage is non-linear and is in favor of the current. Yes or no? So if we are above VT for VGS, we are in an amplification mode here. If VGS change a little bit, the current will go very high. Yes or no? See? The input voltage here, VGS, and the output is on the other terminal. VGS is between the gate and the source. Yes or no? That's the input. But the output is here. Yes or no? Between the drain and the source. See, that's why we call it transistor. Transistor. You see? I promised you that I will explain to you why we call it transistor, and today we got the opportunity to call it. So transistor, look at here, transistor. So transistor has two parts. Has trans means transfer. Transfer or something that moves from one side to another side. And resistor actually comes from the word resistor. Here there is resistor stuff and all these things, but here just to say that the voltage of one side controls the current of the other side. You understand? So it's like we are transferring the resistor on the other side. You understand? Transferring the resistor on the other terminal. You understand? Because the terminal, the control voltage, is actually on a terminal that is different from the output terminal, which is here the drain. Okay? So we are transferring that resistance. And that's the origin of the word transistor. You can go also to Google and go to Wikipedia to enjoy that. But that's the thing. So it's not ID-VDS, it's ID-VGS. VGS is between the gate and the source. So if we have to draw, if I draw, for example, for you here, let's draw something here. Bingo, bingo. Okay, I will put an arrow for you. Okay, this is the source. So the voltage here between this terminal and this terminal, see, this is the gate, is controlling the current that is coming from this terminal to this terminal. That's amazing. Yes or no? So it's not on the same terminal. In the diode, if you remember the diode, we have exponential, yes or no? We said if the voltage change a little bit, the current go very high, yes or no? Remember the diode? Who revised that? You revised that for sure. For the quiz, huh? For the midterm, yes or no? Very good. So here is the same story, yes or no? But it's different in the sense of ID of the diode and VD of the diode, they are across the same terminals, yes or no? But in the story of the MOSFET, they are decoupled. You understand? There are two different terminals here. They share the same ground, yes, fine. Same terminal here, but this voltage is there and the current is there. See how beautiful this device is? Very, very interesting device. Later on you will appreciate. But that's exactly why we call it a transistor. Transistor. But because when we pronounce it very hard, transistor, and that's it. We eat something in between. Okay, clear? Cool. Any question? Any question? It's fun, huh? Isn't it? It's fun. Just we pay attention and we enjoy our life. Alright, good. So now we have a nice, nonlinear equation. The input there, the output there. The output can go very high, very fast up when this guy changes by a little bit, and that's the origin of the amplification. This will not happen. This will not happen if we are not in the saturation. Yes or no? That's the only place in the transfer curve of the MOSFET, or not in the transfer, in the characteristic, IV characteristic of the MOSFET when this happens. Doesn't happen in the triode. Alright. Some storms like we have today. Alright, why? Because this is very important. Look at this. There is a resistor there that has disappeared. And that's for a reason there. So what you see here is actually the large signal model of the transistor. We said that any device that we study, we have to have its model, like we did with the diode. Yes or no? We do also the same for the transistor. And that model is based on the behavior, how that transistor works. That's what it is. Let's look. Okay, we have three terminals. We start by the terminals, the gate, the source, and the drain. Yes or no? Do we have any current that goes from the gate to the source or drain? That's why there is no wire there, or resistor or whatsoever. Yes or no? So we call it floating. There's nothing that connects it to anything. Yes or no? So the current there is zero. Yes or no? Why it's zero? Why the current at the gate is zero? Because, Harry, raise your hand. Yes? So what's between the gate and the others? What do we have? Who knows? Raise your hand, yes? No, there is no diode between the gate and the other parts. There is something else. Yeah, but what do we have between the gate and the other parts? Can somebody tell me? Yes, Nasra? Very good. There is an insulator. You forgot that insulator? And that insulator is what? Is the oxide. It is silicon dioxide. We said that, huh? Of course, the revision will help. But alhamdulillah, there is no revision. Okay, thanks, Nasr. Good enough? Alright, good. So we have there an oxide between the gate and the drain source. Very good, excellent. Now, that's number one. Now the controlling voltage here, as we said, is VGS, yes or no? That's the control. This model works only where? In saturation. And that's the model. We don't have a model, we do maybe, but it's not in our course, okay? Here, this model only for saturation, it's not for triode. So, the input voltage or the controlling voltage is VGS. And the output is IDS, the current between the drain and the source. And this symbol is the symbol of what? Current source. This is how much that the current source is equal to this voltage minus VT squared multiplied by the rest. You get this current. Done. Clear? Yes or no? That's it. We are just describing, the model describes the device. It just tells you how the device works. And that's what the model tells us. Yes or no? We know this model when it works. It has to be in saturation. And there is no connection between the gate and the other terminals because there is an insulator, which is the oxide. Salamat salak, we are done. Here there was a resistor, yes or no? That resistor, what does it do basically? Here that resistor is super high resistor. Why? Because that resistor is actually the device that will relate the current ID with voltage here. But because in saturation the voltage VDS does not control the current, this resistor is either does not exist because there is no current between them that depends on the voltage of VDS, or is so high that we can say it's open. Yes or no? So the resistance here between the drain and the source is super high. Why? Because if there was a resistor here, if we put any resistor here, we can assume also there is a current there. Yes or no? Because there is a voltage. Yes or no? And if there is a voltage, there is a resistor, there must be a current there. But that current is actually relates the voltage here with the current here. But in saturation, VDS does not control the ID. Yes or no? So that means there is no resistor. Yes or no? See how we tricked you? Or there is super high resistor here that it will eliminate any current that goes between them because of this voltage. I see I'm talking to myself. I repeat? If I need to repeat, fine. Ask. That's fine. Absolutely. Okay, let's do it. If I will draw now. Follow me. I will. Maybe this will help better. If I have here a voltage, let's call it VDS. Let's say VDS. Any voltage. Let's say VDS in our case. And I have between this terminal, of course, this will be drain and this will be source. Back to blue. Okay. If we have here a resistor, so automatically there is no question about it. I trust Ohm's law. So VDS is actually delta V. Remember that. So I say VDS divided by R will give me ID. Yes or no? Boom, boom. That's it. Okay. Now, if the resistor is super high, so there will be no current going through. Yes or no? It's like open circuit. We know that too. So, what we know, and that's in green now, is that in saturation, do we have any relation between IDS and VDS? Do we have any function between them? There's no function, yes or no? Because in saturation, the drain current depends only on overdrive voltage, yes or no? It doesn't depend at all by VDS. Did you see that? That's what we said since the morning. Yes. Cool? With me? Very good. So there is no function I will write here is not equal. There is no relation between them. If there is no relation between them, that means there is no resistance between them. Got it now? There is no resistance. If there was a resistance, there would be a relation. Yes or no? All the resistance is super high, basically. It's extremely high that there is no relation between them. If the resistance is too high, we have what we call open circuit. Yes or no? You know that, This is basic. We are tired after the exams, I can see that. You are dead, basically. Are you with me? Is it clear? I repeated, you didn't repeat or something. Very good. So that's what it is. So that resistance is so high that basically we can neglect it. So there is no resistance between them. This current depends only on this voltage. The resistance there, RDS, is infinity. That's it. And to know that the resistance is infinity, we go to bar. Okay, very good. If we come to this board again, we say that, okay, R, I will say R, okay, will be equal to what? Usually is dVs, or delta VDS, over delta IDS, yes or no? In saturation, ID does not depend on VDS, it's actually constant, yes or no? So delta IDS is equal to what? It's constant, yes or no? So delta is equal to 0. MX R2. So this is another way to express that. Mathematically. That's why math. Okay? Good. So we can explain that physically, electronically, as well as mathematically. And that's the beauty of microelectronics. Good. Other problems. We have a problem here to solve. Let's do it quickly and together. You like that, There's no tutorial in this course. Allahumma lak alhamd. The college decided that is not useful. Good luck for all of you. It's actually never happened in any course in the world to have an engineering course without tutorial. But there's a smart one in the college, so he said that, you don't need that. Good luck with him. Okay, so let's solve that together. And let that guy enjoy his life. And let us suffer. Anyways. So what do we have here? We have a problem here. Says that we have an NMOS transistor fabricated in 0.18 micron process. When we, how do we call a process? Process means fabrication technology. All right, remember that. Write it down. A process is a fabrication technology. It's always named after the minimum length of that technology because the transistor has a length. Yes or no? The minimum length that the technology can fabricate the transistor, that will be the name of that technology. So we call 0.18 micron, so automatically is that the minimum length? 0.18 micron. Alas, clear? Excellent. So, and he's giving us that L is using the LME. Thank you. W given. First the technology is specified by COS given. Mu N given. VT given. Pay attention to the units. Huh? They are in red because they are touchy. Touchy means be careful. Don't take them lightly. Okay. Find VGS and VDS. We solved this same problem last time. Yes or no? The first part. Yes or no? And we solved it basically by knowing that we are at the edge of saturation. Go back to the video, you'll know what I'm talking about. Alas? So we said that the first question we need to know is where the transistor is working. From there we use the equation and then the solution will be like sleek. مثل كيف اسمه الفجر مثل غسق الفجر عنده وحدة اسمها رايح بالعربي يلا نسيناه لما نفكر على الله توكلنا. So from this equation, from this question, as we solved it last time, we can know easily VGS and VDS. Yes or no? Excellent. So we're not going to waste our time. Now the question here is, if VGS is kept constant, so if we keep VGS constant, that means what? We don't know. How do we know trial? How do you know that's trial? We don't know. It's nice try, but it's not. Because we know the condition for trial. We did not see anything about that, yeah? We didn't say VDS, below, blah, blah, blah. We didn't say. But we said constant. If we kept VGS constant, that means we kept what? What is related to VGS? No, it is not dependent on the VGS. Is what VGS? What do we get from VGS? We get? No, it's independent. VGS and VGS, they are totally. V what? Maybe yes, maybe. But there's another parameter right away we get. V over drive. Because V over drive is VGS minus VT. So that means we are keeping V over drive constant. This is proof that the exams have done a big job for you. Cleared your memory and you look tired. I've seen someone is sleeping right now. But anyways, so we keep now the overdrive constant. So find VDS, that result in the ID is equal to 50 microamp. Yes or no? Where the MOSFET is. If we have how much? 3 minutes. In 3 minutes, if someone tell me this, 10 bonus marks. Right now, 3 minutes. Go ahead. Where the MOSFET is, and raise your hand and quickly let me know that. Who knows? Raise your hand. Yes. And why? Yeah? You don't say. You have to say yes. Where is it? In trial. Very good. Excellent. Because the current. Because the current decreased, so we are in triode. Why? Thank you very much. Another try. I will not comment on her answer until after 3 minutes. 10 bonus grades. Who said more? 15 bonus marks. Okay, who said more? Huh? Looking around. You're reading the notes. That's cheating. That's cheating. Don't read the notes. Look at the board. Look at the board. No, President. Take the. You're also accountable. Don't read anything. Where do we know now the MOSFET? Where is the MOSFET? Just from this equation. Look at the equation here and here. Less than half minutes. Yes? We don't know even quadratically. How did you know? Nice try, but it's not. We don't know. The answer is in the board. Yes, go ahead. But in saturation, where in saturation? So what in saturation? It can be anywhere in saturation, yes or no? So if it, if it is below, thank you very much. Excellent, you got 15. 15 bonus, that's it. What's your name? Write your name after the class, okay? I take your name and I give you 15 bonus mark, you got it. That's it, thank you very much. And that's the way. Look here, it's very easy. What she said makes sense also. But this is also very, very trivial. Look here. In the question here, look here. The MOSFET operating at the edge of saturation. At the edge. At where? At 100 micron, yes or no? And then here where? So it's like zzz, it's going down, yes or no? If it is at the edge and is going down, it must be automatically where? Automatically in class. This is how smart she is. And she got free lunch, 15 grades, in your bonds. Send me an email, or I'll take your name. So you got her answer? It's clear?
Sir,
Yes, go ahead.
Aisha said the same answer.
Who? No. She did not. No, I know. No. She did not, and you cannot defend her. She did not explain the reason being that it is decreasing. But she did not mention that she is going from the saturation to triode because we were at the borders actually. Yes or no? It's not VDS that is decreasing. It's actually the current is decreasing from the boundary here of the saturation and the triode. That's it. I am treating everybody here the same. Okay? So, it's clear to me who deserves it. Now, back to business. So now here, how to solve this equation? How to solve this equation? To find VDS, we do what? We use the equation for triode in this case. Yes or no? Because we know that is in triode now. Thanks to that smart one. So in that case, we get to the board and we write the equation that is ID is equal to how much? Kn prime W over L. There's okay, good. And then V over drive minus half VDS times VDS. Yes or no? I'm not expecting you to memorize this, but I will give it to you in the equation sheet of the exam. Now, we know ID, yes or no? We know ID. It's given. See it. 50 micron. K prime is given. W over L is given. V over drive, do we know that? Yeah, from the same. That's why he said we're keeping the same VGS. That means we use the same overdrive. See why? See how we read the question now? Now we use the overdrive that we have here. Because once we have a VGS, we can get the overdrive. Yes or no? So bingo. So now we know everything except VDS, and that's the second order equation. Yes or no? How many solutions to that? 3. 0, 2, 4, 5, 2. Very good. So we have to. We will find 2. There's no question about it. So one of them does not make sense. Yes or no? Must be. And which one will not make sense? VDS control what? Control where the MOSFET is. Yes or no? Because already VGS is above VT. So we are in either triode or saturation. But the question here, VDS that we will accept is the one that will make sure that our MOSFET is in triode. Yes or no? Because we are in triode in this equation. Yes or no? We know it. So VDS, the one that we will accept there, is the one that makes sure that the MOSFET is in triode, not in saturation. Okay? And we can know that if VDS above the overdrive, it's in saturation. If it is below, we are in triode, and that's the one that we will accept from these two solutions. Of course, this example is also solved in the textbook, so you can have a look at that as well. Alright, to investigate the use of MOSFET as a linear amplifier, let it be operating in saturation. Okay, so we are going to investigate how the amplifier works. So the MOSFET, we have to put it where? In saturation. Yes or no? Clear? Good. So, and we are given VDS. Does VDS control that current? No, but we are giving VDS. Thank you very much. No problem. Find the change in ID resulting from VGS changing from 0.7 volt by 0.01 or minus 0.01. What does it mean? We go and we draw something. So let's draw now the characteristic of our transistor. Yes or no? So this is ID or IDS, and this is VDS. Let's say the overdrive is here, so that's the boundary between the triode and saturation. And we are in saturation, and VDS actually was here, for example. This value of VDS is equal to 0.3 volt, let's say that. the question. So we are trying just to see how to answer this question. Very good, excellent. Excellent. So what do we do? The question is, we are going to change VGS, yes or no? From this by this and this. If we change VGS, what happens? The curve has to change, yes or no? Because each curve, this is for a given overdrive, yes or no? This is the overdrive of how much? This is the overdrive that corresponds to 0.7 minus VT. What is VT? Here. So that overdrive is equal to 0.2. Very good. So this is that we have to start. We are starting from the overdrive equal to 0.2 volt. Now, if VGS increased by 0.02, the overdrive increased by how much? By the same thing. The difference is VT. So that means we will be on a different curve. I will draw it here in red. Will be like, for example, it's not exactly the same, but this will be therefore 0.2 plus 0.01. Yes or no? Of course, volt. And if the overdrive change by very good, by minus 0.01, will be also in a lower also. In lower, why? Because ID in saturation actually is proportional to overdrive, yes or no? If it increase, it will be squared, yes or no? So it has to decrease, and we are in a curve where the overdrive, so let me go back here. So this is how much is the overdrive in this case, and here the overdrive in this case, yes or no? So it's 0.2 minus 0.01. So here the question therefore is asking us what is this difference of voltage, and that difference of voltage is delta I. That's the question here that is asking us. So to investigate, find the change in ID. That's the question. You understand? That's the question. Find the change. If there is a change, there is a delta automatically. Yes or no? Clear? And that's the delta we are referring to. That distance between the two. Does it change here when VDS change? It does not, because the current in saturation does not depend on VDS. Yes or no? So whether it's at 0.3 or 0.4 or 0.1 million, it doesn't matter. It's the same distance because they are parallel. Yes or no? VDS does not change the current in saturation. Correct? Good. Very good. How to find delta IDS? Any idea about how to find it? The change in ID? Anyone? I see some people are using the other course to solve the problems in this course. So any idea how to find delta ID? How to find delta ID from the graph? Can somebody tell me? Think about it. Yes, go ahead. Do you have any idea how to solve it? Throw any idea. Make mistakes. You will learn. What's that? No. Which one? Did you understand how I draw this? So the green one is correspond to the IDS when the overdrive is 0.2 minus 0.01. And then boom, that's the one. It's easy, huh? That's exactly the solution. Why? Because the point here, this one, we know how to get ID, yes or no? ID, I will write it in red, so that we are on the same curve, talking about the same curve. So we know ID there, or IDS is equal to half Kn, not Kn prime, because I put W over L there. The overdrive, this one, let's call the overdrive 1, the overdrive 1 squared, yes or no? Now for the second one, the green here, we can get that one as well. ID, IDS is equal to half Kn prime, the overdrive, we call it 2 here, so that will make sure. Square, yes or no? That's it. Do we know the overdrive? We know. We know Kn. So ID minus ID, boom. You have the delta ID, yes or no? Simple. There is another way. So you go this way, there's nothing magic about it. She was tired, she barely could see the board, but it was so obvious for her to solve it. Yes or no? Correct, Asma? Very good, excellent. Now, if we go to another solution, we know, I show you this shows you the beauty of math. In saturation, we have IDS is equal to what? Half Kn V over drive squared. Yes or no? Yes or no? Look at this beauty. Let's make differentiation both sides. Delta delta. This is correct. Yes or no? Good. Very good. So we continue now in. So this is constant. Yes or no? This in these things are constant. Yes or no? So they stay out. Yes or no? Now delta is only on V over drive square. Yes or no? The differentiation of x square, we know it, is 2. V over drive here. V over drive here is the nominal, is the average, is the one in between them. Yes or no? Is the average. Is the average, average, whatever it is. And then delta V over drive. Yes or no? That's what it is. This is math. Yes or no? Very good. The answer is this one. Yes or no? That's what we are looking for. Yes or no? This is what we are looking for. Let's keep going. That's it. So the overdrive that we have here is corresponding to the overdrive of 0.7, which is actually 0.2. Yes or no? The delta overdrive between the two curves, let's go back to the two curves. How is delta overdrive between the two? It's very easy actually. We have 001 up and minus 001. So delta overdrive is how much? 002. Yes or no? That's it. So this is 002. This is 02. Of course the multiplication. And these two stay here. Kn we know it. Alpha we know it. We are done. In a simple mathematical way and in without calculating that quadratic twice and headache. That's the way I suggested. The textbook suggests it differently. Correct? Look at the textbook, you'll see. But this shows you how important math is in your course. It's very important to look and to use mathematics. Very important, makes your life much easier. Okay, good. Any question about this? Straightforward, that is like magic. Boom, boom. So as an engineer, we always look at finding the solution with the cheapest way. Basically getting caviar or seafood with shawarma price. I go to Carrefour, give me seafood with 5 dirhams, for example. If you are joking, go get one. You tell him, I'm an engineer. Oh, what's that? He doesn't understand that. That's the getting a seafood with the shawarma price. Okay, got it? Very easy, but boom, to the point. Even better than the textbook. Alright, good. Alright, so let's keep going. Alright. Now we touch something a little bit interesting, and we will finish it very quickly actually. Alright, so far we assume that IDS is absolutely independent of VDS. Yes or no? And therefore, any change in VDS will not cause anything, a change in IDS, the drain current. And that's what we found, that RS, or the channel resistance between these, is infinite. Yes or no? I've shown you that in an equation. So basically, there is absolutely no resistance between them, and that's, in practice, is completely untrue. That's not the case. That's also idealistic. That's a wishful thinking. Okay, wishful thinking, but we hope that. But in practice, this is not the case. Still, VDS has some influence. I'll show you that in the next. So basically, why VDS must actually, so before we did not include the effect of that, well, because the model was simple and we need to start something. So to see that VDS has an influence on IDS is basically we have to go back to the pinch off. When the pinch off happens, it happens at the boundary. The pinch off is the phenomena that basically happens when the channel disappears from the drain, start to disappear there, and it starts at the boundary between triode and the saturation. Means when VDS is equal to V overdrive and the channel starts to disappear from there onwards. Okay, so after the pinch off, what will happen? Now that's the question is asked in here. So basically it says it will cause the pinch off point to move slightly away from the drain, and that's what we said as well. Why? Because the more you increase the drain, the more that pinch off will be more towards the source, and that's why that tip point of the channel will go towards the source. Okay, but it doesn't stop the current from flowing. It's just the channel starts to disappear from the drain area. Okay. So basically, the voltage across the channel, which is now shorter, what will happen to that? Will remain at overdrive. So basically, the channel itself, it remains at the overdrive, but the length has shortened thanks to the VDS. So in conclusion to that, we say that basically the additional voltage that we have applied on VDS to push the pinch off point away from the drain basically will be seen as a new depletion region. Is like a depletion region that is making the channel away and throwing the charge away from the drain. This is what physically is happening. So that's in terms of that. So basically we say that now the channel has changed in length from initially L, which is the distance between the source and drain, to another distance that is L minus delta L, which is caused by the drain voltage. So we say that the channel length is modulated by the drain voltage, yes or no? Modulated means what? Means controlled, okay? So the drain voltage is controlling now the channel length. And the channel length happens to be in the equation of the current, yes or no? In the saturation. Do we have L there? We have L. L in that equation is the length of the channel, okay? Now L has changed by delta L. Who caused that? Is VDS. So VDS caused the change in L, and L is in the current equation, so the current has to change. So VDS control L, L control I, so that means VDS control also I. Logic, yes or no? And that's what we call the channel length modulation, and that's what actually makes VDS control the current in saturation. We are a little bit contradicting ourselves, but that's the reality, okay? That is the reality. Alright, in that case we must put a resistor actually now between the drain and the source, and we call it from now on R naught. Naught means عقدة. R عقدة, R naught or R0 some people, and we can represent that R naught in the equation. So initially we had ID in saturation is equal to something over drive square, yes or no? But now we will take all of that something and we'll multiply it by a new factor that is 1 plus lambda VDS. Why we put it this way? To see how, or to basically to include the channel length modulation that VDS, so before it was controlling L, so we'll tell him, okay, fine, we'll use the same L, but we will give you here, your effect will include it in a certain parameter, lambda VDS. Okay? So that's the trick. Instead of changing L based on VDS, we keep L and we include VDS there through lambda, and lambda is the parameter that describes the channel length modulation. I think we are getting a little bit to the edge and we are tired and we need to stop. Yes or no? Enough, sir. Thank you very much. Any question? We'll continue inshallah from next class, from this point onwards. Please make a revision and we'll take it from here and we continue. Thank you very much.